2 seconds. That is all it takes. An F/A-18 Super Hornet, a 33-ton machine carrying fuel, weapons, and pilot, sits at the bow of a Nimitz-class carrier, engines already at full military power. The flight deck crew steps clear. The Catapult fires. In less time than it takes to blink twice, that aircraft goes from a standing start to 165 miles per hour, and it is airborne over the Pacific. The system that does this is driven by superheated steam, and it has been doing exactly this since the 1950s. Here is the paradox. The United States Navy spent more than $13 billion developing a replacement for that steam catapult. The new system, EMALS, the electromagnetic aircraft launch system, uses linear electric motors, digital control, and technology that did not exist when the steam rig was bolted into the first carrier deck. By every engineering principle, EMALS should be superior, more precise, more controllable, ready for the future. So why does a 70-year-old steam track still launch the fleet's most expensive aircraft more reliably than its billion-dollar successor? And why does that question matter far beyond one carrier program, reaching all the way to what the Navy can and cannot put in the air over the Western Pacific for the next 20 years? The answer runs through physics, maintenance culture, the economics of naval aviation, and a strategic choice that naval planners in Washington are still wrestling with today. Stay with this, because the answer changes depending on which layer you peel back first. The steam catapult did not arrive fully formed. It was itself a revolution, developed in the early 1950s by a British engineer named Colin Mitchell and licensed by the United States Navy, which installed its first operational version, the C-11, aboard USS Hancock in 1954. The C-13, the variant that became standard on Nimitz-class carriers, entered service in the 1970s and has been refined ever since. It works on a principle that is almost elegant in its brutality. A piston in a slot running the length of the flight deck is driven forward by a surge of high-pressure steam stored in accumulator tanks below. The piston hooks to the aircraft via a launch bar. Steam releases. The aircraft goes. What the C-13 has going for it is not sophistication. It is repetition. 50 years of operational data. Tens of thousands of launches across a dozen carriers. Maintenance crews who can diagnose a faulty valve by sound. Spare parts that exist in quantity. Procedures drilled into every catapult officer until the sequence is reflex rather than thought. On a Nimitz-class carrier at surge operations, the kind of flight tempo a conflict in the Western Pacific would demand, the C-13 can cycle an aircraft roughly every 60 seconds. That is the clock the Navy plans around. The cost of that steam is real and worth naming. Each catapult shot consumes approximately 1,000 pounds of fresh water, converted to steam and vented. A carrier distills its own fresh water from seawater using the reactor's heat, so the marginal cost per shot is measured in energy and time, not dollars. But at high tempo, 100 launches in a day. That is 50 tons of fresh water consumed by the catapult system alone. The logistics are manageable, but not free. And the steam comes from the same nuclear plant that powers everything else on the ship, which means catapult operations and other high-power demands compete for the same thermal budget. Here is what is most surprising about the steam catapult's longevity. It is not the hardware that makes it hard to replace. It is the institutional knowledge wrapped around that hardware. Nimitz-class carriers carry roughly 5,000 personnel. Of those, the catapult and arresting gear division numbers in the dozens. They are specialists trained over years, and what they know about the C-13 is not written down completely anywhere. It lives in hands and habits. That kind of knowledge does not transfer automatically when you bolt in a new system. Which brings us to what the Navy decided to build instead. EMALS, the electromagnetic aircraft launch system, is installed aboard USS Gerald R. Ford, the lead ship of the Ford class, commissioned in 2017. The system replaces steam pressure with a linear induction motor, a long track of electromagnets that accelerate a carriage, and the aircraft attached to it, using precisely controlled electrical pulses. The power comes from a set of energy storage devices called rotary energy storage systems, essentially large flywheels that spin up between launches and discharge during the shot. The engineering case for EMALS is genuine. Because the electromagnetic force can be modulated digitally throughout the stroke, the catapult can vary the energy it delivers with a precision that steam cannot match. A steam catapult delivers a sharp initial spike of force that is then modulated mechanically, roughly. EMALS ramps up more smoothly and can be tuned in real time to match the specific weight and speed requirement of each aircraft. For a heavy, fully armed F/A-18 Super Hornet, that difference matters at the margins. For a lightweight drone, the kind the Navy expects to be operating in large numbers by the 2030s, that difference is not marginal. It is the difference between a successful launch and an airframe that absorbs forces it was not built to survive. That is the future the Navy was buying with $13 billion, not a better catapult for the F/A-18. A catapult that can throw the aircraft, the F/A-18's replacement will fly alongside. The problem is what happened between the design and the delivery. USS Gerald R. Ford was delivered in 2017 after years of delays and cost overruns. EMALS and the Advanced Arresting Gear, AAG, the system that catches returning aircraft, were both identified early as the primary drivers of those cost increases. During the ship's post-delivery testing period, the reliability numbers for EMALS drew serious attention from the Pentagon's testing office. Mean cycles between critical failures. The number of launches the system completes before a failure that would abort a mission came in well below the design target. The Navy's requirement was for EMALS to achieve roughly 4,000 mean cycles between critical failures. Early operational testing data pointed to numbers in the hundreds. I went through the Director of Operational Test and Evaluation reports from the Ford's early years, and one number kept coming back. In some testing periods, EMALS was logging critical failures at a rate that would be operationally unacceptable in high-tempo combat conditions. The system was not dangerous in the way a structural failure is dangerous. It was unreliable in the way a machine tool is unreliable when it is still being debugged, which is an acceptable condition in a factory. It is a much harder condition to accept on the only carrier commissioned in the Ford class, sailing toward a contested operating environment. Put yourself in the position of a strike group commander for a moment. You have one Ford-class carrier with EMALS, and you have 8 Nimitz-class carriers with C-13 steam catapults. You are planning for a sustained operation in the Western Pacific, the kind of operation where sortie rate is not a statistic but a survival condition. Which system do you want under your flight deck? The Ford program's cost story does not end with EMALS development. Gerald R. Ford herself cost approximately $13.3 billion to build, more than double the cost of the last Nimitz-class carrier, USS George H.W. Bush. A Nimitz-class carrier runs roughly $7 to $8 billion at current estimates, depending on configuration year. The difference is largely attributable to the new systems. EMALS, AAG, and the dual-band radar, all introduced simultaneously on the lead ship, compounding integration risk. Naval procurement has a principle that experienced program managers will cite, and that program timelines consistently ignore. Do not introduce multiple new technologies simultaneously on a lead ship if you can avoid it. The learning curve for each system is steep. The interaction effects between new systems are unpredictable, and the lead ship always absorbs the highest cost because it is where all the debugging happens. Gerald Ford absorbed a great deal of debugging. What strikes me about this program is not that the technology failed. It did not fail in any fundamental sense, and EMALS has improved substantially since initial delivery. What strikes me is that the Navy essentially chose to run a full-scale operational test of 3 major new systems simultaneously on the first ship of a class intended to set the carrier standard for the next 50 years. The pressure to modernize, the budget cycles, the competitive timeline against Beijing's carrier program, all of those forces pushed toward doing everything at once. The bill came due in delayed deployments and a reliability record that took years to improve. The Nimitz-class carriers, meanwhile, kept sailing. USS Nimitz herself, commissioned in 1975, is still on active deployment rotations. USS Carl Vinson, USS Theodore Roosevelt, USS Abraham Lincoln. These are the ships actually covering the Western Pacific right now, with C-13 catapults that their crews can fix with tools and knowledge they have had for decades. Here is the part that does not make sense on the surface. The Navy knew all of this going in. The risk assessment for the Ford program flagged EMALS integration as a high-risk item years before commissioning. The decision to proceed was not made in ignorance. It was made in the context of a timeline problem, a judgment that waiting for each technology to mature before introducing the next one would push the Ford class into a time frame that the strategic competition with China's expanding carrier program made unacceptable. In 2015, China commissioned Liaoning, its first carrier, a rebuilt Soviet hull that functioned more as a training platform than a strike asset. In 2019, Shandong followed. China's first domestically built carrier, still using a ski jump ramp rather than a catapult, limiting the weapons loads and fuel states of departing aircraft. But Fujian, the Type 003 carrier launched in 2022, changed the equation. Fujian is equipped with electromagnetic catapults, China's own version of EMALS, and it is the first Chinese carrier capable of launching aircraft in a configuration comparable to American full-deck operations. Beijing shipbuilders moved from a ski jump carrier to an electromagnetic catapult carrier in less than a decade. American naval planners watching that timeline understood that the era of uncontested American catapult superiority in the Pacific was closing. The Ford class and EMALS were, in part, a hedge against a future in which China's carrier aviation caught up technically. a bet that the investment in electromagnetic launch technology would eventually yield a capability gap that a ski jump competitor could not bridge. This is where the two Catapult technologies stop being a competition between old and new and start being a choice between two different futures for carrier aviation. Here is a take that will probably draw some disagreement. The reliability problems with EMALS were not primarily an engineering failure. They were a program management failure that was then framed as an engineering failure, because the engineering is more specific and less embarrassing to fix. The decision to deliver Gerald Ford with systems that were not operationally mature was a political and budgetary decision, driven by commitment timelines and contractor incentives and congressional schedules. The engineers who built EMALS knew the system needed more development time. The program did not give it to them. The distinction matters because it changes what lesson the Navy draws from the experience. If EMALS failed because the technology is fundamentally unreliable, the conclusion is to extend steam catapults indefinitely and accept the limitations that come with them. If EMALS struggled because it was delivered before it was ready, the conclusion is different. The technology is sound, the process was flawed, and the fleet's job now is to accumulate the operational experience that makes EMALS as reliable as the C-13. The data from Gerald Ford's later operational periods supports the second interpretation. Mean cycles between critical failures for EMALS have improved substantially since the ship's early years. The system that logged failures in the hundreds of cycles in 2017 testing has moved toward the thousands of cycles range in more recent reports. That improvement is the product of exactly the kind of learning that happens when you operate a system at sea rather than in a test facility. This matters for a specific reason. The Navy has 4 Ford-class carriers either in commission, under construction, or on order: USS Gerald R. Ford, USS John F. Kennedy, USS Enterprise, and USS Doris Miller. All 4 will carry EMALS. None of them will have a C-13. Which means the institutional knowledge base for electromagnetic catapult operation is accumulating right now, ship by ship and deployment by deployment, whether the early reliability record was encouraging or not. Does that institutional investment in EMALS justify the early unreliability the fleet absorbed, or was there a smarter path that preserved steam longer while the new system matured in a less operationally critical environment? That question does not have an obvious answer, and people who work these systems professionally still debate it. The drone question sharpens the argument considerably. The MQ-25 Stingray, the Navy's carrier-based unmanned tanker, currently in development and testing, is designed to be launched by Catapult. In its tanker configuration, it is not a particularly heavy aircraft. But the next generation of carrier-based unmanned systems that naval planners expect to be operating by the mid-2030s includes strike-capable drones that will need to be thrown into the air at a range of weights and configurations that a steam catapult cannot reliably accommodate. The C-13's control is mechanical. The launch energy is set before the shot and cannot be finely adjusted during it. For a 33-ton Super Hornet, the variation in launch energy relative to the aircraft's total inertia is small enough to be manageable. For a lighter drone, the same variation becomes a larger percentage of the aircraft's total energy budget, and the mechanical imprecision of a steam shot can stress airframe structures designed for a gentler acceleration curve. EMALS can modulate that curve in real time. The C-13 cannot. This is the actual strategic argument for EMALS. Not that it is better at launching F/A-18S, though it may be gentler on their airframes over time, but that it is the only catapult that can launch the full range of aircraft the Navy intends to put on carrier decks in the 2030s. The investment is not in today's flight deck. It is in the flight deck that has to operate alongside MQ-25 Stingray tankers, next-generation unmanned combat air vehicles, and whatever the follow-on to the F/A-18 turns out to be. The catapults do not operate in isolation. The choice is embedded in a broader maintenance and logistics ecosystem that shapes everything from deployment length to crew workload to the cost per flight hour of every aircraft that leaves the deck. The C-13 on a Nimitz-class carrier requires significant maintenance infrastructure. The steam systems, the accumulators, the piping, the valves, the piston assemblies need regular inspection and periodic overhaul. The catapult maintenance crews are trained specialists who spend years learning the system's particular behaviours and failure modes. When a C-13 has a problem at sea, the people who fix it are already on board with the tools and the parts. The supply chain for C-13 components is mature and well stocked. The institutional playbook for every foreseeable failure mode is written and memorised. EMALS on the Ford class has a different maintenance profile. The system is more complex electrically and requires different diagnostic tools and different training. The energy storage systems, the rotary flywheels, are a maintenance item that has no direct analogue in the steam world. The software that controls launch energy is updated and modified in ways that steam system procedures never were. The crew expertise needed to keep EMALS operational at sea is still being developed in real time across the ships that carry it. A detail that stuck with me going through the operational test reports. In some early Ford operational periods, the time required to recover from an EMALS critical failure was long enough that it would have been operationally disqualifying in a high-intensity conflict scenario, not because the system could not be fixed, but because the recovery time exceeded the tactical window available. A steam catapult failure is typically faster to diagnose and reroute, partly because the failure modes are simpler and more familiar, and partly because the crew has been fixing C-13 problems for decades and has the process down to a reflex. That gap has narrowed. The Ford's crew has now accumulated years of EMALS experience, and the mean time to recover from failures has improved alongside the mean time between them. But the comparison illustrates why experienced maintenance officers on Nimitz-class carriers watch the EMALS data with a combination of professional interest and something that looks a great deal like relief that they are not the ones managing the transition right now. The economic comparison between the two systems is not straightforward because the costs land in different places. A C-13 steam catapult is essentially a sunk cost on a Nimitz-class carrier. The hardware is paid for, the maintenance is folded into the ship's operating budget, and the per-shot cost in steam is absorbed by the reactor. EMALS required the $13 billion development investment that is now amortized across the Ford class. Over 4 ships, that is roughly $3 billion per hull in development cost before the first aircraft is launched. EMALS proponents argue that the system will reduce airframe maintenance costs over time by delivering gentler, more consistent launch forces. Each F/A-18 Super Hornet has a finite number of catapult launch cycles built into its structural life. Harsher launches consume that life faster. If EMALS genuinely extends airframe life across the carrier air wing, and the data from Ford is beginning to suggest it does, then the per-flight hour cost calculation shifts in EMALS' favour over the long service lives of the aircraft it launches. The math here is not settled. Airframe life accounting is complex, and the actual savings will depend on how the Navy uses the aircraft over their operational lives and how maintenance cycles play out. But the argument is serious, and it is one reason the Navy has not revisited the decision to standardise on EMALS for the Ford class despite the early reliability struggles. The strategic frame for all of this is the Western Pacific, and specifically the anti-access and area denial problem that Chinese military planners have spent 20 years building around American carrier operations. The DF-21D and DF-26 anti-ship ballistic missiles, weapons designed to threaten carrier strike groups at ranges of 1,500 kilometres and beyond, define the operating envelope that any American carrier commander has to account for. A carrier inside that threat envelope operates under constraints that did not exist during the Cold War. The flight deck tempo that determines the carrier's offensive value, how many sorties it can generate per day, how quickly it can cycle aircraft, how many different types of aircraft it can launch, directly affects the strategic calculus of whether that carrier can accomplish its mission faster than the threat can locate and engage it. This is where the catapult question connects to the broadest level of Pacific strategy. A Nimitz-class carrier with C-13 catapults operates a flight wing of roughly 60 to 70 aircraft, predominantly F/A-18 Super Hornets and E/A-18G Growler electronic attack aircraft, with an MH-60 helicopter complement and a small number of specialised aircraft. The C-13 launches all of them reliably. But it cannot launch the MQ-25 Stingray effectively in all configurations, and it cannot launch the next generation of heavier unmanned combat vehicles at all in their expected weight ranges. A Ford-class carrier with EMALS operates the same core air wing today, but it is the platform that will integrate the MQ-25 first, and it is designed to carry the next generation unmanned systems that could extend the carrier's strike range well beyond what manned aviation alone can achieve. The unmanned aircraft that naval planners are designing for the 2030s carrier wing are intended to operate at ranges and in threat environments that reduce the risk to manned aircrew, flying further, staying longer, accepting attrition rates that no manned aircraft mission can accept. EMALS is the enabler for all of that. Beijing's naval planners are watching the same dynamic. Fujian's electromagnetic catapults give Chinese carrier aviation a capability that Liaoning and Shandong do not have. The ability to launch aircraft at full fuel and weapons loads without the penalty imposed by a ski jump ramp. But Fujian's catapult system is still being tested, and its operational reliability is not publicly documented. The gap between having an electromagnetic catapult and operating one reliably at sea at high tempo is exactly the gap USS Gerald R. Ford has spent the last several years closing. China's Fujian is now in the position Gerald Ford was in 2017, a ship with sophisticated new launch technology that has not yet been stress-tested by sustained operational deployment. There is a pointed irony in that parallel. The United States developed EMALS, ran it through a difficult early operational period, absorbed the criticism and the cost overruns, and is now accumulating the experience that makes the system operationally credible. China observed that process and chose to develop its own electromagnetic catapult. A technology decision that acknowledges the American bet on electromagnetic launch was correct, even if the execution was expensive. The question for Chinese naval aviation now is whether they can compress the learning curve that the Ford program had to climb the hard way. Naval analysts watching the Western Pacific tend to frame this as a race, and it is, but not quite the race that carrier count numbers suggest. China now operates 3 carriers and has additional hulls under construction. The United States operates 11 carriers, all nuclear-powered, with the global logistics and basing infrastructure that has supported American carrier aviation for 80 years. Raw numbers favour the United States substantially. But the race that matters for the 2030s is not the carrier count. It is the carrier capability. Specifically, which fleet first achieves reliable, high-tempo electromagnetic catapult operations integrated with unmanned aircraft at operationally meaningful scale. The United States has a head start in electromagnetic catapult experience. China has demonstrated it can close technology gaps faster than most Western analysts expected. Both fleets are working toward a carrier aviation model that neither has fully achieved yet. Comment why yes or no. Does China's Fujian close the carrier capability gap with American Ford-class carriers by 2030? We read every comment, and the breakdown from people with actual naval knowledge is always the most interesting read on these videos. The 11 American carriers do not all sail simultaneously. At any given time, maintenance cycles, yard periods, crew rotations, and training requirements mean that roughly 4 to 6 carriers are available for deployment. The coverage requirements of the Western Pacific, the Mediterranean, and other standing commitments mean that the number of carriers that can surge to a single theatre on short notice is smaller than the headline number suggests. The catapult reliability of every carrier in that surge count directly affects the sortie rate available to the theatre commander. One detail that has stayed with me through this analysis, the Navy's requirement for EMALS reliability. 4,000 mean cycles between critical failures, was chosen in part because it matches the operational cadence expected during a sustained high-intensity conflict. 4,000 launches at 60 launches per day is roughly 67 days of sustained flight operations. The assumption embedded in that requirement is that a major Pacific conflict would demand that kind of tempo. Designing a catapult system to that requirement is a statement about what the Navy expects carrier aviation to have to do if deterrence fails. The C-13 on a Nimitz-class carrier does not have a published mean cycles between critical failures number in the same sense, partly because the data accumulated over 50 years of operation has been folded into maintenance procedures rather than tracked as a single metric. The anecdotal operational record is strong, but the maintenance burden to achieve that record is also real. And on an aging hull, maintaining a catapult system designed in the 1970s consumes maintenance hours and shipyard time that could theoretically be spent elsewhere. The Navy's shipbuilding budget is under pressure from multiple directions simultaneously. The cost of Ford-class carriers, the cost of Virginia-class attack submarines, the cost of the DDG-X destroyer program intended to succeed the Arleigh-Burke class. All of these are competing for a defense budget that has its own political constraints in Washington. The Ford class was supposed to deliver savings over time by reducing crew size. The Nimitz class requires roughly 5,000 personnel to operate. The Ford class was designed to operate with closer to 4,500, using automation to reduce the manning requirement for systems like the catapult and arresting gear. In practice, achieving those manning reductions has taken longer than planned, partly because operating new systems at sea requires more people during the learning phase than during steady-state operations. The savings are real in principle. They have been slower to materialize in practice. The political economy of carrier aviation intersects with the catapult choice in one specific way that rarely gets discussed. Nimitz-class carriers will be in service until at least the 2030s for most hulls and into the 2040s for the newer ones. USS George Washington, commissioned in 1992, is the most recent to undergo a full midlife refueling and complex overhaul, a multi-year shipyard period that extends a nuclear carrier's service life by decades. When a Nimitz-class carrier goes through that overhaul, the question of whether to upgrade its catapult systems is at least theoretically on the table. The answer to date has been no. The cost and complexity of retrofitting EMALS into a hull not designed for it exceeds the operational benefit for a ship that still has decades of life on its C-13. But that calculation will look different in 10 years when the Ford class has accumulated more operational experience and the next generation of drones is actively seeking deck space. What resolves the paradox at the center of this story is not a declaration that one system is better. It is the recognition that the two systems are answers to different questions. The C-13 is the answer to, how do you reliably launch everything in today's carrier air wing at maximum operational tempo with minimum maintenance risk? The answer is 50 years of refinement and the accumulated knowledge of every catapult division in the fleet. It is a very good answer to that question. EMALS is the answer to a different question. How do you build a catapult that can launch everything the carrier air wing will contain in 2035, including unmanned aircraft that a steam rig cannot safely throw? The answer involves linear electric motors and digital control and energy storage systems and a development program that costs $13 billion and a reliability curve that is still being climbed. It is also a very good answer to that question, just a more expensive and slower one, and one that required absorbing operational pain that the steam catapult's advocates found difficult to justify. The Navy's actual position. Sustaining C-13 operations on 10 Nimitz-class carriers while accumulating EMALS experience on the Ford class and its successors is not indecision. It is a portfolio hedge. The steam catapult covers the near-term operational requirement. EMALS covers the long-term capability requirement. The cost of running both systems simultaneously across an 11-carrier fleet is real and not trivial. But the cost of committing entirely to one before the other has proven itself in every dimension would be higher. The strategic price of this transition is paid in ways that do not show up cleanly in procurement budgets. Every sailor in a Ford-class catapult division who masters EMALS is building the institutional base that the next Ford-class crew will inherit. Every deployment the Gerald R. Ford completes adds to the operational data set that informs the reliability requirements for USS John F. Kennedy and the carriers behind her. Every MQ-25 Stingray test launch from a carrier deck refines the launch parameters that EMALS will need to handle when the unmanned air wing is not a test program but an operational reality. That learning is not free. It is paid in crew hours and maintenance cycles and the professional stress of operating a system that is still being understood. The Nimitz-class crews who sail past in their steam-launched Super Hornets are not operating an inferior system. They are operating a mature system that earned its reliability through exactly the same learning process. It just happened before most of them were born. The DF-21D and DF-26 missiles that define the threat environment for American carriers in the Western Pacific are indifferent to whether the aircraft they are designed to threaten are launched by steam or by electromagnets. What they are not indifferent to is the range at which those aircraft can strike, the sortie rate at which they can operate, and whether unmanned aircraft can extend the carrier's reach into threat envelopes where manned aircraft cannot go. Those variables, range, tempo, unmanned integration, are what EMALS is designed to enable. The catapult choice is not about the fight today. It is about the fight the Navy expects to have to deter or win in the decade after next. Which brings the question back to where it started. The flight deck, the steam, the 2-second launch. On a Nimitz-class carrier today, an F/A-18 Super Hornet sits in tension at the end of a C-13 catapult track that has been doing this since before the pilot's parents were born. The system fires. The aircraft goes. The process is so well understood, so deeply practiced, that it looks almost routine, which is the highest praise you can give a piece of military hardware that operates in an environment where nothing is actually routine. On USS Gerald R. Ford, the same moment looks different. The EMALS track is quieter. There is no steam cloud on the same scale. The launch is smoother. The data system logs every parameter of every shot. The crew is still learning things about this machine that the C-13 crews learned decades ago, and they are learning them on deployment, in real conditions, building the record that will eventually make EMALS as unremarkable as the steam rig it is replacing. The open question is not which catapult is better. It is whether the Navy can afford the transition cost. In dollars, in reliability risk, in crew workload, in the strategic exposure of operating a maturing system alongside a mature one across 11 carriers and the vast distances of the Pacific, at the pace the competition requires. Every year that EMALS improves, the case for accelerating the transition strengthens. Every deployment where a Nimitz-class carrier launches 100 sorties without a catapult aboard, the case for staying the course on steam strengthens too. The catapult choice is not made once and then settled. It is made every time a program manager decides whether to retrofit, every time a deployment schedule is set, every time an unmanned aircraft test program asks for deck space on a carrier that can or cannot throw it safely. And it is made in the shadow of a competitor who watched the American electromagnetic catapult struggle through its early years and decided to build one anyway. Because the Americans, for all the cost and the problems, were clearly building the right thing. 11 carriers. 2 catapult technologies. One future fleet that has to work in a Pacific that is less permissive than any American carrier has operated in since 1945. Does the Navy ride the proven steam rig until EMALS matures fully, protecting today's sortie rate at the cost of tomorrow's capabilities? Or does it eat the remaining transition cost now, pushing EMALS experience across the force faster, and own the only catapult that can launch the carrier wing the 2030s will require? Each path carries its own bill, and the choice is being made right now. One launch at a time. If you want to see how the Ford class stacks up against the rest of the Navy's shipbuilding gambles, and what the DDGX destroyer program says about where American naval power is actually going, that breakdown is next.